Let's continue with 3 today, products and quotient of vector spaces. So first, 3.71, we have the definition. If you have V1 through Vn, all of these are vector spaces. We're going to define V1 times V2 times da 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 Vn as lists of vectors from each one of these vector spaces. So V1, V2, da da da, Vn, where V1 is from the first vector space, V2 is from the second vector space, and then so on. Okay. Now, also define let's say you have one element which is V1 da 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 Vn, and another element that looks like this, but let's use a different letter because these are different vectors. So if you have that, you define this as V1 plus U1, Vn plus Un. Then you see that this is again in the product space. So I should really have titled this product space. So this is again in the product space because since V1 and U1 are from the first vector space, V1 plus U1 is also in the first vector space, and so on and so on. Vn and Un are both in Vn, so their sum should still be in here. And therefore, the resulting vector meets all the conditions for being in the product, right? So that's a well-defined operation on this product space. And if you had some constant in the ground field, base field, then again you define this as lambda times V1, da da da, lambda times Vn. And again, because each of these are vectors in vector spaces, and vector spaces are closed under scalar multiplication, all of these are individually in all these vector spaces, so this resulting element does lie in this product space. So using these vector addition and scalar multiplication, you can check that this set with these operations satisfy all the axioms for being a vector space. And that's what 3.73 says. So 3.73 says the above is a vector space and the book just skips the proof and says it's left to the reader, and I also don't want to do this. It's just really boring. You just have to write everything, and almost everything is just pretty straightforward. I can't see the real value of proving this, so we'll just accept that that's true. But instead, let's think about some examples. So the textbook has some nice examples. For example, 3.72 has a P2R product with R3. Okay, let's try to find out what this vector space is. Okay, what are the generic elements of P2R? P2R is a collection of
polynomials with degree 2 or less?
Yeah, so they all look like a1 x squared plus a2 x plus a3. Okay. And then what's a generic element in R3?
XYZ.
XYZ. So you collect this as a list, and these lists become each element in this set. This is a set of all of these lists, where A1, A2, A3, and X, Y, Z, all of these are real numbers. So what's a specific example of such a thing? Can you come up with a just one specific element that looks like this? So e.g., what are some stuff that looks like that?
X squared plus 5x.
X squared plus 5x plus 1, 3, 2, 5. That's one, right? Now, I don't know where it was, but later in the textbook, it asks for the basis. So, what's the basis? Well, think about set of vectors that will generate everything that's written here. Well, we can have x squared 0, 0, 0, x 0, 0, 0, 1, 0, 0, 0, and then I'm going to put a list here, so let's just write here, and then 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. So that's going to be the basis for this vector space. How do you know anything in this space is in the span of that? How do you know? Well, this itself, then a1x squared plus a2x plus a3 comma xyz. Oh, sorry, I shouldn't be using xyz here, because I'm using x here, right? Sorry about that, but let's put b1, b2, b3. I was being careful, I'm sorry. b1, b2, b3. Okay, so the generic element, so anything in here looks like this, can be written as a1 times x squared 0, 0, 0 plus a2 times x 0, 0, 0, a3 times 1, 0, 0, 0, and then what? b1 times, let's see if you are following my logic here, b1 times
0, 1, 0, 0.
0, 1, 0, 0, b2 times 0, 0, 1, 0, plus b3 times 0, 0, 0, 1. Right? It's true, because if you just do the scalar multiplication that we defined, well, I erased it, but it's here. The scalar multiplication that we defined, which means whatever you multiply in front, you just multiply to each individual one. So when a1 is outside, you can bring it inside and make it as a1x squared. A2x, A3. And when you add these up, you end up creating A1x squared plus A2x plus A3. Right? So on and so on. So you add everything, you'll see that these two are indeed exactly the same. And because this is in the span, well, let's call this as the basis, okay? Span of B, you see that this list is going to span the entire space. And then the next thing is to show that if this linear combination is equal to 0, each A1, A2, A3, B1, B2, B3 are 0, but that's also pretty straightforward because if you rewrite this into this form and require that that's equal to 0, comma 0, 0, 0, then this has to be equal to 0 polynomial, this has to be equal to 0, 0, 0, so you're forced to say A1 is 0, A2 is 0, A3 is 0, B1 is 0, B2 is 0, B3 is 0, and you're done, okay? All right, so that should kind of give you an idea of what this product space is. And there are some nuances here. So 7.34, first of all, you can see that R cross R is equal to R squared. That's because Rn is really, the definition of Rn is really the product set. So you learn this not in the vector space, not in this linear algebra course. You learned this in the set theory class, which was the proof theory class, MAT 200. So there you learn this. And but it's by definition these are the same. Now let's see why. What is R cross R? Well, this is a collection of a real number, some real number, and another real number, right? Where x is in R and y is also in R. So if you look at the definition over there with R and R each being one-dimensional vector spaces, this is what you get, but that's exactly the definition of R2, right? So we know that these two are the same. Now, we have to be a little careful. There are two different meanings of the cross. One is the product set, and the other is the product space. Okay. Product set would be thinking of R and R individually as sets, and product space would be thinking of these two as vector spaces. Now, if you write them in set theory notation, they're actually exactly the same thing, except that if you think of these as vector spaces, then this one has additional vector addition and scalar multiplication. Okay. So the problem is, if I just think of this product as a product of sets, then this one wouldn't have these two operations, and therefore these two will be equal as sets. But if you we're thinking of R2 as a vector space in this context, so yeah, you should really, when I'm writing this down, I'm not just writing down that they're equal as sets, but including these addition and multiplication, they're exactly the same thing. Now, on the other hand, if you do R2 cross R3, this is not equal to R5. Now that's a bit strange, but if you write down the definition, then you kind of see why, because what's in R2? R2 is something that looks like xy, right? What's in R3? That's something that looks like ABC, right? And then what does the product space contain? Well, it collects lists of vectors, one vector from the first space, another vector from the second space, right? So this left side would be same as this with x, y, a, b, c being real numbers, right? So that's what you have. But if you look at R5, R5 by definition it means R cross R cross R cross R cross R cross R. And this one, according to the definition we wrote down, will be x, y, a, b, c with x, y, a, b, c, and R. Okay, so see, the elements in here are lists of lists, or tuples of tuples, tuples of tuples, whereas this element in here is the list of length 5 list of real numbers. That's what's in R5. Of course, if you define a map, let's say some f that sends R2, that's defined from R2 times R2 cross R3 to R5, where it sends x, y, a, b, c to x, y, a, b, c. Okay. Then this is both injective and surjective. So this is what we just learned in the previous section as a isomorphism. Okay, so there's an isomorphism between these two vector spaces, and you can even say this is a very natural one too. Like you could have so many different isomorphisms between these two, but amongst all of possible isomorphisms you can write between them, this is the most natural one, right? Yeah. So there's a natural isomorphism between the two. You can say these are naturally isomorphic. And in the textbook, it just says that this is a relabeling map. You're just writing the same sequence of numbers with different notations. It's saying it's a relabeling map. Okay, so all of this discussion says two things. So number one, R2 cross R3 is not equal to R5. However, number two, R2 cross R3 is isomorphic to R5. Okay. So you have to know those distinctions, right? Okay, the first meaningful theorem in this part of product spaces is the fact that the dimension of the product space is the sum of the dimensions that make up the product space. Now, the book just explains this in words, and if you remember our basis for P2R cross R3, we just picked some basis for here, and you kind of see how to go about this. You take all the basis, 1, x, and x squared, and there were E1, E2, E3, those two standard bases from here. So do you remember what the length of the basis was? What was the length of the basis for this guy?
It's 4.
No, it was
6.
6, right? It was 6, because I had 3 for this guy and 3 for this guy. So it was the length, total length was 6, and because the basis has length 6, what's the dimension?
6.
6, right? Whereas this is 3, and that's also 3, because this one has A1, A2, A3, B1, B2, B3, so this individually they're dimension 3. So you can see that even here, dimension of the product space is 6 because it's 3 plus 3. And that's just a generalization of what we just observed here. So you can show it like that in words. You could also use like a double indices like the following. We can say that let V1 1, V1 2, da da da, V1 N1 be the basis for V1, okay, and then V2 1, V2 2, da da da, V2 N2, where N2 is just some other another number. So by writing like this, I'm really saying that the dimension of V1 is N1. And if I write like this, I'm saying dimension of V2 is N2. Okay? Be the basis for V2, all the way down to V1. I used N here, so I should really be using M, sorry. M1 and M2. Okay, so this nth, it's V2, Vn, Mn, be the basis for Vn. Okay. So you might hate this notation because usually you're thinking of putting something here means it's exponents, right? But when you go to higher mathematics or some physics, a lot of these numbers on top does not mean it's exponent, but it's rather an index. And only when you have parentheses and then something, that's when it's an exponent. Okay. All right. So if you do that, then what you do is then you define the basis as V1 comma 0 0 V1 1 V1 2 comma 0 all the way up till V1 N1 M1 0. Oh, but that's just the start. Now you have these, and then the next one, the list will be 0 comma V2 1 0 0 comma V2 2, and then 0 comma V2 M2, just like that, and all the way down until you have 0 0, and then you have Vmn1, and then until you get 0 0 0 Vn Mn. Okay. And then you show that this is the basis, and this will be length M1, this will be length M2, this will be length Mn, so the total length will be M1 plus M2 plus until Mn, so that it will be the, once you show that this is a basis, then that's going to give you the dimension for this product space, and on the right side it will be m1 plus m2 until mn. So that's what 3.76 is trying to say. If you don't like this, because it's not rigorous enough, I would say you can go about proving this by using induction instead. So to use induction, what you can do is you can first show that if you have V1 cross Vn cross Vn plus 1, that's naturally isomorphic to V1 until Vn plus 1. You can show that these two are naturally isomorphic because there's a natural isomorphism between them. So you can just prove this theorem for two sets. So step 1, prove for dimension of V1 times V2 is dimension of V1 plus dimension of V2. And for this one, the notation is not simpler because let's say basis for V1 is V1 through I'll say U1 through UN, U1 through UM, and then B2 would be the basis for the second guy, which is W1 through WK, where M will be the dimension of V1 and K will be the dimension of V2. Then you just say that the base that you make by putting U1 comma 0 all the way up till UM comma 0, and then comma 0 comma V1, W1, all the way up till 0 comma WK is going to form a basis for this space. You just show that, and because the notation is a lot simpler than that one, it's not so hard to write this. And once you prove this, then you can now apply this thing to itself. If it's true, then the above theorem is true for V1 cross V2 cross V3 because you can rewrite this as V1 cross V2 cross V3, just like that. Okay. So we already know that the theorem is true for this guy, and then you just apply this again. So this part could be like a lemma, where you just apply it for the base case, and then for the induction step, you just apply it again and again. So that's like, I don't want to write that because that's also pretty convoluted. But it's, yeah, either way, so I do see that either approach you take is somewhat hard to write down, so that's why the textbook just wrote some words and expected the readers to understand what's going on. But it is what it is, okay? So we'll just accept that this is proved using these methods. Okay, 0.77. Oh. Okay. All right, 3.77. Let U1 through UN be subspaces of V. Okay? Define gamma as a map from U1 cross cross UN to U1 plus U2, well, U1 until UN. What are the elements in here? Well, the elements in here are, take a vector U1 from U1, and then you just pick arbitrary vectors from each one of these vector spaces, right? Subspaces. So it's like this. Hopefully that you do notice that I'm writing capital U here and lowercase u here. It's hard to write upper and lower correctly on a whiteboard. Okay, and then we send this to u1 plus da 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 un. Okay. Now we are going to accept that this is a linear map. So let's skip that part. Okay, so this is a linear map. Proof left to the reader. Okay. Since the product space is a vector space and sum of subspaces again a vector space, you can talk about linear maps between those two vector spaces. So you can check that that's true. Now the core of 3.77 is saying that u1 plus da 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 un is a direct sum if and only if gamma is injective. Okay. And that part it should be worthy of proving, because that's less straightforward than showing that this is a linear map. So let's try to prove it. Okay, proof. So assume, let's do this part, which means assume u1 plus da 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 un is a direct sum. Okay. Now we also know that being injective is same thing as showing that the null space is just 0, right? So we want to show that. Okay, so suppose some V is in the null space of gamma, because how do you show that a given set only has one element? Well, you just pick an arbitrary element and show that no matter what you try, it always turns out to be 0, then it has to be this one. Okay, so that's the way we're going to do the argument. So well, what's in the null space? Well, first of all, gamma has the domain as the product set, so V would look like u1, u2, da 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 un, right? With gamma of V equal to 0. Okay. But then, if you investigate this further, what does gamma of this do? It just simply adds them up, right? And this, we also learned that something is a direct sum if and only if. So maybe I should number this. So this one here is a direct sum if and only if u1 plus da 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 un equals to 0 means u1 is 0 all the way up till un is 0. So these two are equivalent, and these two are equivalent. So the strategy I'm taking is instead of showing that this implies that, I'm trying to show that this implies that. Okay, so but then this is what this means. This, okay, just plugging this into V and then applying our map just gives you that. Then this is true, and U1 plus here now it's a capital U. U1 through UN. These are lowercase. Okay, being a direct sum. Sum implies that U1 is 0, U2 is 0. These are now lowercase as well. Okay. And we have V equals to 0, comma 0, comma 0. Since we have everything 0, that's what we get, which is 0, so that the null space of gamma is just this. That proves this direction. Okay, what about this direction? Again, instead of showing this, let's show this. Okay, so suppose U1 plus da 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 UN is equal to 0. Okay? And then using the fact that it's injective, we have to come up with this, right? Yeah. Then gamma of U1 da 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 UN is 0, right? Because that's the left side, right? According to this definition. Right? Since gamma is injective, null space of gamma is just 0, so that U1 through UN is equal to 0 everywhere. And that means U1 is 0, U2 is 0, all the way until UN equals to 0, which finishes that it's a direct sum. Okay? All right, so since I need both of these, I'm not going to erase anything, but let me just write down a corollary, which is also pretty important. So 3.78 corollary is that U1 plus da 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 UN, these are capitals now. I wish there was a way to distinguish capitals and lowercase more effectively. UN is a direct sum if and only if dimension of U1 plus da 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 UN is equal to dimension of U1 da 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 dimension of UN. Let's just see why it's a corollary. I don't want to write it down, but it should make sense. First, going this way. If U1 through UN adding is a direct sum, then we know that this is injective, right? Now, not only is injective, me see. I didn't show that it's surjective. Surjective is because, well, if I use the fundamental theorem of linear maps, then the dimension of this is equal to the dimension of the null space plus the range, right? And we know that the dimension is here, right? And therefore, that implies that the dimension of this guy is equal to the dimension of this, which is equal to that. That's how this direction is done. Okay? Should I write it down? Maybe I should write it down. First, this way. Yeah, I just realized something that in other textbooks, the fundamental theorem of linear maps is also known as rank nullity theorem. Rank nullity. And the reason for that is because the formula says dimension of V is equal to dimension of the null space of T plus dimension of the range of T. And this dimension of the range of T is known as the rank of a linear map. Okay? And the dimension of the null space is called the nullity. And if you add them, you get the dimension of your domain. So that's sometimes known as the rank nullity theorem. So if I apply that to this thing that we just proved, if we know that it's a direct sum, we know that null of gamma is 0, so this one will be, if I specialize to this case, it'll be dimension of u1 cross until un is dimension of the null of this gamma map that we just defined plus the dimension of the range of gamma. And since the assumption is it's a direct sum, we see that this is equal to 0 because direct sum is injective. So now you have, and the range is this guy, so you have and also this is same as this one, so dimension of u1 plus dimension until dimension of un equals to dimension of u1 plus until un. What I didn't say clearly is that this gamma map is surjective because no matter what element you take from here, they always look like this, right? Some u1 from u1 and un from un, right? But whatever vector you pick from here, you can always put it into a list of vectors like that and apply gamma to it to target that. So this map is obviously surjective, okay? So when we said gamma is injective, it means that if it's a direct sum, it's saying that these two are isomorphic. Okay. So if you were working with direct sum and somehow saw that it looks a lot like a product space, the reason is exactly that. It's if you have a direct sum, then these two spaces are isomorphic, okay, under this isomorphism. Okay, so sorry, I knew I had to say something about surjectivity. I forgot that part. All right, so now this other direction would be if this is true, then it's direct sum. Well, in this case, what you do is you apply FTLM, but this time, since this is same as this, and this is same as that, and they are equal by our assumption, that forces the nullity to be 0. The dimension of the null of gamma would be 0. So the nullity is 0, so the null space is just the 0 space, and therefore you can apply this 3.77 with the gamma being injective, and therefore it's direct sum. Okay, so both sides are just the corollary of these two put together with the fundamental theorem of linear maps. Okay, so that's how this portion is proved.